In mathematics, the free group Fs over a given set S consists of all expressions that can be built from members of S. Considering two expressions different unless their equality follows from the group axioms, the members of S are called generators of Fs. An arbitrary group G is called free if it is isomorphic to Fs for some subset S of G, that is, if there is a subset S of G such that every element of G can be written in one and only one way as a product of finitely many elements of S and their inverses. A related but different notion is a free abelian group. Both notions are particular instances of a free object from universal algebra. History. Free groups first arose in the study of hyperbolic geometry, as examples of fusion groups. In an 1882 paper, Walther von Dijk pointed out that these groups have the simplest possible presentations. The algebraic study of free groups was initiated by Jacob Nielsen in 1924, who gave them their name and established many of their basic properties. Max then realized the connection with topology, and obtained the first proof of the full Nielsen-Schreier theorem. Otto Schreier published an algebraic proof of this result in 1927, and Kurt Riedermeister included a comprehensive treatment of free groups in his 1932 book on combinatorial topology. Later on in the 1930s, Wilhelm Magnus discovered the connection between the lower central series of free groups and free Lie algebras. Examples. The group of integers is free. We can take S equals 1. A free group on a two-element set S occurs in the proof of the Banach-Tarski paradox and is described there. On the other hand, any non-trivial finite group cannot be free, since the elements of a free generating set of a free group have infinite order. In algebraic topology, the fundamental group of a bouquet of K-circles is the free group on a set of K elements. Construction. The free group Fs with free generating set S can be constructed as follows. S is a set of symbols, and we suppose for every S in S there is a corresponding inverse symbol S-1 in a set S-1. Let T equals SS-1, and define a word in S to be any written product of elements of T. That is, a word in S is an element of the monoid generated by T. The empty word is the word with no symbols at all. For example, if S equals A, B, C, then T equals A, A-1, B, B-1, C, C-1, and is a word in S. If an element of S lies immediately next to its inverse, the word may be simplified by omitting the S, S-1 pair. A word that cannot be simplified further is called reduced. The free group Fs is defined to be the group of all reduced words in S, with concatenation of words as group operation. The identity is the empty word. A word is called cyclically reduced if its first and last letter are not inverse to each other. Every word is conjugate to a cyclically reduced word, and a cyclically reduced conjugate of a cyclically reduced word is a cyclic permutation of the letters in the word. For instance, B-1 ABCB is not cyclically reduced, but is conjugate to ABC, which is cyclically reduced. The only cyclically reduced conjugates of ABC are ABC, BCA, and CAB. Universal property. The free group Fs is the universal group generated by the set S. This can be formalized by the following universal property. Given any function f from S to a group G, there exists a unique homomorphism phi Fsg, making the following diagram commute. That is, homomorphisms Fsg are in one-to-one correspondence with functions Sg. For a non-free group, the presence of relations would restrict the possible images of the generators under a homomorphism. To construct phi for given f, first note that phi sends the empty word to identity of G and it has to agree with f on the elements of S. For the remaining words, phi can be uniquely extended since it is a homomorphism, i.e., phi equals phi phi. The above property characterizes free groups up to isomorphism, and is sometimes used as an alternative definition. It is known as the universal property of free groups, and the generating set S is called a basis for Fs. The basis for a free group is not uniquely determined, being characterized by a universal property as the standard feature of free objects in universal algebra. In the language of category theory, the construction of the free group is a functor from the category of sets to the category of groups. This functor is left adjoint to the forgetful functor from groups to sets. Facts and theorems. Some properties of free groups follow readily from the definition. Any group G is the homomorphic image of some free group F. Let S be a set of generators of G. The natural map Fg is an epimorphism, which proves the claim. Equivalently, G is isomorphic to a quotient group of some free group F. The kernel of F is a set of relations in the presentation of G. If S can be chosen to be finite here, then G is called finitely generated. If S has more than one element, then F is not abelian, and in fact the center of F is trivial. Two free groups F and F are isomorphic if and only if S and T have the same cardinality. This cardinality is called the rank of the free group F. Thus for every cardinal number k, there is, up to isomorphism, exactly one free group of rank k. A free group of finite rank n greater than 1 has an exponential growth rate of order 2n-1. A few other related results are the Nielsen-Schreier theorem. Every subgroup of a free group is free. A free group of rank k clearly has subgroups of every rank less than k. Less obviously, a free group of rank at least 2 has subgroups of all countable ranks. The commutator subgroup of a free group of rank k greater than 1 has infinite rank. For example, for F, it is freely generated by the commutators am, bn, for non-zero m and n. The free group in 2 elements is square universal. The above follows as any square universal group has subgroups of all countable ranks. Any group that acts on a tree, freely and preserving the orientation, is a free group of countable rank. The Cayley graph of a free group of finite rank, with respect to a free generating set, is a tree on which the group acts freely, preserving the orientation. The groupoid approach to these results, given in the work by P.J. Higgins below, is kind of extracted from an approach using covering spaces. It allows more powerful results, for example on Gruszko's theorem, and a normal form for the fundamental groupoid of a graph of groups. In this approach there is considerable use of free groupoids on a directed graph. Gruszko's theorem has the consequence that if a subset B of a free group F on n elements generates F and has n elements, then B generates F freely. Free abelian group. The free abelian group on a set S is defined via its universal property in the analogous way, with obvious modifications. Consider a pair, where F is an abelian group and phi SF is a function. F is said to be the free abelian group on S with respect to phi if for any abelian group G and any function psi Sg, there exists a unique homomorphism Fg such that F equals psi for all S in S. The free abelian group on S can be explicitly identified as the free group F modulo the subgroup generated by its commutators, F, i.e., its abelianization. In other words, the free abelian group on S is the set of words that are distinguished only up to the order of letters. The rank of a free group can therefore also be defined as the rank of its abelianization as a free abelian group. Tarski's problems. Around 1945, Alfred Tarski asked whether the free groups on 2 or more generators have the same first-order theory, and whether this theory is decidable. Seller answered the first question by showing that any 2 non-abelian free groups have the same first-order theory. and Karlampovich and Myazanov answered both questions, showing that this theory is decidable. A similar unsolved question in free probability theory asks whether the von Neumann group algebras of any two non-abelian finitely generated free groups are isomorphic.